In this video, we are going to talk about how to use Mathematica to integrate functions that don't have very nice antiderivatives for us, so that we can still attribute some meaning to the area underneath these curves without having to do a lot of heavy computation or without necessarily knowing an antiderivative of the function. So one really great application of this is actually to probability theory, where we have this probability function which makes a normal curve for us. So you may have heard that word thrown around before, a normal curve. If you look at a lot of random samples and things in life and then plot them, they often fall in this so-called normal distribution, which is defined by a very nice but messy formula. So for example, the example we're going to be looking at today, if you take a bunch of people and they all take a test, and then you plot along the x-axis their different test score, and you plot along the y-axis the number of people receiving that test score, it will often form a curve that very much resembles this normal distribution. If you then translate that to a continuous case, it ends up looking a lot like this curve, which has a horrendous formula that they've put here into the textbook. So it has something generally to do. In its nicest form, it looks like this. 1 over the square root of 2 pi e to the negative x squared over 2. If you want to take into account some other things, like having a mean that they're just going to indicate with a mu and a standard deviation. So mean is like your average, and your standard deviation is a measure of how spread out the curve is. Right? So that's changing the standard deviation and changing the mean. Just shifts it. Let's put it back right there. If you want to be able to shift where that average is and how spread out this function is, you can generalize the function in this really very messy for us way. But as you can see, being able to take a look at this probability function is really useful, because if we can attribute a value to the area underneath one of these curves, it will tell us the probability of a test score, for example, falling within a particular range. So that's the example we want to do today. We want to take a look at, supposing that the scores on a test are normally distributed, the average test score is 500 and the standard deviation is 100. We want to then use that really messy curve above to find the probability that a person scores between 450 and 650 on the exam. And when you look at the solution that they provide in the textbook, they say we just use a computer algebra system to do this. So that's what we'd like to do. We'd like to open up Mathematica and teach Mathematica this messy formula that we have up here once and for all, and then we'd like to ask Mathematica to do the integration for us. So let's open up Mathematica. And let's get Mathematica going with a basic computation. And next, let's set about entering in that really messy function into Mathematica. Now, I'm just going to call the function little f, but that function is actually a function of several variables. So when we look back at the textbook, there's an x, which is our actual variable, and then there's these other unknown constants that we need to enter in at the time that we run the function, which are the mu, which are the mean, where this vertical line is, and the standard deviation, which tells us how fat or skinny the curve is. So we'd like to go into Mathematica and define a function f of 3 variables. The first variable is x, the second variable we'll call m for the mean, and the last variable we'll call s for the standard deviation. And we want to copy that function as we see it in the textbook, so let's open up our math palette so that we can have an easier time entering it in. Let's take a look again. The first thing I need is a fraction, 1 over the s square root of 2 pi. Let's get that entered in. I need a fraction, 1 over s times the square root of 2 pi. And that's the coefficient on my function. Then I need to raise e to this fractional power. So let's do that next. Let's then take e, raise it to a power, and that power is a fraction. The numerator is the quantity x minus mu squared, and then we put a negative sign in front of it. So we'll do the quantity x minus the mean, and we'll square that, and then put our minus sign out in front. Let's figure out the denominator, which is 2 times the s squared. And that whole big bad thing is our function for Mathematica. Now, once we've gone ahead and put that into Mathematica, what we want to know is when our mu is equal to 500, so that m we defined as 500, and the standard deviation sigma, which is our s, is 100. If we plug in those values for m and s, we want to find the probability that a test chosen at random has a score between 450 and 650. We want to find the integral of that function we've just entered from 450 to 650. And that'll tell us the probability. So let's go ahead and see if we can get Mathematica to do that. Now, the first thing I'm going to do is I'm going to say, I don't happen to know, this looks horrible, it's got lots of letters in it, but I don't happen to know an antiderivative for that off the top of my head. And so maybe I could just ask Mathematica. Mathematica is very smart. Maybe Mathematica knows an antiderivative for my function f of x ms. If I integrate it with respect to if I integrate it with respect to x, perhaps Mathematica will know an antiderivative. So I can ask Mathematica, but it just gives me this crazy nonsense. And maybe I could come up here and say, okay, Mathematica, I'd like to know the integral of that when m is equal to 500 and s is equal to 100, then just integrate that function, if only one letter is there. And it looks just as bad. I could even ask Mathematica to integrate that function. Ultimately, we want to integrate that function as x goes from 450 to 600. Is it 600? 650, excuse me. And type it in, but Mathematica gives me this function, which is not very helpful to me. So the secret to this is, not only do I not know how to integrate that function, Mathematica doesn't really know how to integrate that function. And if we want a numerical value here to tell us and help represent a probability, we need to tell Mathematica that we want it not to try to integrate that function as in using the fundamental theorem of calculus, but we want Mathematica to integrate that function like a computer. Just do a Riemann sum and don't tell us about it. So we have to tell Mathematica to numerically integrate our function. Our function is f of x, our mean is 500, and our standard deviation is 100. And then we'd like our computer to integrate that from 450 to 650 to give us that probability. And just using the NIntegrate function instead of the integrate function, if we now hit enter, Mathematica tells us about 62%. So simply using that numerical integrate command in Mathematica is enough for us to go from getting this horrible but exact answer to getting an answer that's much more useful to us contextually, which says about a 62.5% chance that you're going to get a score within these values. And notice too that this is the exact answer that the book comes up with for part B, the probability of a random score lying in this range of values, 62.5%.